All right, also 9.2 support. And really, this is just a refresher on solving certain types of equations. So for this first one, they want us to solve 4 over z plus 3 equals 3 over z minus 6. So this is just to get us a refresher on solving an equation when you got a fraction equal to a fraction. And our goal is to get rid of the fraction so we can solve for this variable. So y'all, when you got a fraction equal to a fraction, we're going to use this property that says when I got a fraction equal to a fraction, we cross multiply this. So to cross multiply, the top of one side multiplies by the bottom of the other side. So I would do my a times d. That's going to equal the bottom of the first fraction times the top of the second fraction. So that'll give me b times c. So to eliminate the fractions in this pattern, we're just going to cross multiply, okay? So here we go. We're going to take the top of the first fraction, 4, and we're going to multiply by the bottom of the second fraction, z minus 6. So that's going to give me 4 times z minus 6. Now, I got to take the bottom of the first fraction times the top of the second fraction. So that'll be 3 times z plus 3. Now, the reason I'm using parentheses, this 4 has to multiply by both of these. And then this 3 has to multiply by both of these on the bottom. So that's why I start out using my parentheses. Now, to get rid of parentheses, we're going to distribute on each side. So 4 times z will give us a 4z minus 4 times 6 is 24. Our other side will be 3 times z, which is 3z, plus 3 times 3, which is 9. Now you can eliminate this step if you remember to multiply the 4 times the z, and then the 4 times the negative 6, and then this side 3 times z and 3 times 3. Okay. So now I'm just going to solve this for the z. And I usually always start out with the variables. And I always want to move the smaller variable to the side of the larger variable. So to do that, y'all, I would just subtract my 3z from both sides. And y'all look, 4z minus 3z leaves me 1z minus my 24. Over here, the z's cancel. All that's left is our 9. So my z's good. I got a 1z sitting here, but now I got to move this negative 24. So we'll add 24 to both sides. So now I bring down my z. The 24's cancel on this side. And on the right side, 9 and 24 give us a 33. So fraction equal to a fraction, we're just going to cross multiply those and then solve for the variable. So then we haven't messed with radicals yet. So they wanted us to practice on solving equations with radicals in them. Now remember, radicals are like square roots and cube roots and so on. So for this one, they want me to solve square root of 4x minus 5 equals 1. Now, this 4x minus 5 is all up under this radical. Okay, so our first goal on a radical equation is to get this radical by itself on one side or the other. Well, since all this is under the radical, this radical is technically by itself on the left side. So to undo a radical, so say if we had so n, we call that the index of the radical. Now, if there's not a number there like this one, we automatically assume that number to be a 2. So this would be just a square root. So we don't have to write the 2 for a square root. But if it was a cube root, we'd have to write the 3 and so on. But y'all, to clear a radical, you raise this thing to the exponent that matches the radical's index. So what happens when you raise it to the exponent that matches the index? It cancels that radical out with that exponent, and all that's left is what was under that radical. So we use this property to solve these kind of equations. So it's telling me to raise it to the power that matches my index. So I'm going to take this square root 4x minus 5, and I'm going to square it. But remember, what you do to one side of an equation, you do to the other side. So that means I got to square that 1. So y'all, what happens? This radical is now going to cancel with that exponent, and all that's going to be left is a 4x minus 5 on the left side, which was what was under the radical. And over here, 1 squared would be 1 times 1, which is 1. So y'all look at that, the radical's gone. So now all we got to do is solve for our x. So y'all, to start solving that, I'm going to move to 5 by adding a 5. And I'll get my 4x, 5's cancel. On the right side, 1 plus 5 gives us 6. All right, final step. Divide 4x by 4. So we're going to divide both sides by 4. So the 4's cancel, giving me a 1x. Now, y'all, this one, we cannot divide 6 by 4 because we don't want decimals or mixed fractions. All we really want to do is reduce this. So 6 over 4, if we reduce it by dividing both the top and bottom by 2, 6 over 4 will reduce to a 3/2. Okay, so radicals, get the radical by itself and then raise it to the exponent that matches that index. But I'm going to do a couple more with the radicals. So this one says solve square root of 5x plus 6 equals 13. So y'all notice on this one, this radical is not on this side by itself because we got this plus 6. So notice on this one, the plus 6 is not under the radical like it was a while ago. So to get this radical
Aside the Sakana.
Say what? Oh, I thought I heard something.
Okay, let me get you a John.
So y'all, we're going to subtract 6 from both sides. All right, so that's going to bring down the square root of 5x. 6 is canceled. On the right side, 13 minus the 6.
Hey, John. ER's on the phone.
Give me 7. All right. Now we're happy. The radical's by itself. So now to get rid of the radical, we're going to raise each side to the second power. Remember, there's not a number shown here, so it is definitely a 2. So we're going to square both sides. Y'all guess what? The exponent now cancels out the radical. All that's left is the 5x. On the right side, you're squaring 7. So 7 times 7 is 49. And y'all, all we got to do now to solve that for that x is divide both sides by 5. And y'all notice that pi divided by 5 gives me 1x. All right, this one, let's see, 49 and 5 don't have any common factors that we can reduce. So that's going to stay a 49 over 5. All right, y'all, let's try one more. And then this will sort of be what your support is all about. So y'all, on this one, I'm going to do a cube root of x plus 6. That's all going to equal 2. So notice up here, the number was not under the radical with the variable. This number is under the radical. That means that we got the radical by itself already. So we want to now get rid of that radical. So we're going to take that cube root of x plus 6. So y'all, the exponent that I need to raise both sides to on this one is going to match that index of a 3. So we're going to cube both sides. So by cubing the left side, that cancels that radical again. All that's left is the x plus 6. And y'all on the right side, 2 to the 3rd power. 2 times 2 times 2, which will give us a 8. So radical's gone. So now we just solve for the x. So since our 6 is being added, we will subtract 6 from both sides. So I'll bring down my x. 6 is canceled. So the x will equal 8 minus 6, which is 2. So just a little support, giving you practice, solving those fractional equations, and bringing back memories about the radical equations. So y'all, that'll lead us into our 9.2 college algebra, inverse functions. All right, y'all, let me turn my paper over. Starting to flip up. All righty, so 9.2 inverse functions. So we'll start out finding the inverse of a relation. Then we'll play with what we call a horizontal line test. And finally, we'll find the inverse of a function. Okay. Well, y'all let me see what my chat's got going on. And if you've done everything, I will see you next Tuesday. All righty, y'all. So all right, you too. All right, y'all. So the first one says find the inverse of the relation. So remember, a relation is like a set of ordered pairs. In the beginning, we did relations when we had the domain and the range with the arrows on them. But this time, they're giving me my relation in a set of ordered pairs. So they're giving me, say, 9, -2, first ordered pair. -7, 7. a -3, 9, and then a 5, -5. So to find the inverse of a relation, now remember, this is 4 sets of ordered pairs. And these ordered pairs have the x first and then the y. So this would be an x and a y, x and a y, x and a y. So y'all, to find the inverse of a set of ordered pairs, we simply swap each of the x and y's. So we're going to swap each x and y for the ordered pairs. So for our answer, now y'all, MathLab will give you these nice curvy parentheses. You just got to put all the points in and remember to put commas in between them, okay? So y'all, if I swap the x and y for the first point, that's going to give me a -2 and a 9. So we're just swapping the order. For the second pair, if I swap the order, I would get a 7, -7. For the third one, I would get a 9, -3. And then finally, for my last point, I would get the -5, 5. And then that would be our final answer. And the reason we're getting you used to doing this, we want you to realize that the inverse, all we're going to do is swap the x's and y's around, okay? So to me, inverse almost means like the opposite of. So y'all watch this one they did. They say find an equation of the inverse relation. This time they're sort of going to give me an equation. They're giving me x to the third times y equals a -7. So here we go for our answer. Now remember, I said to find the inverse of a relation, all we do is swap the x and y. So if I swap this x and y around, that'll give me a y to the third x equals -7. Now, y'all, when we swap them, we don't bring the exponent with the x. Because if I move the x to the third and the y, then I don't have an inverse. I just rearranged how they looked. Okay? So if the exponent was on the x in the beginning, the exponent has to be on the y when you find that inverse, okay? All righty, so that was just getting you used to swapping x's and y's around. So what we're going to look at now is what we call the horizontal line test. So here's the thing about an inverse function. If a function has an inverse function, then the actual function has to be what we call 1-to-1. So what I mean by 1-to-1 is that the y values all can only have one x value. So if you remember back in the 2.2, we found out if something was a function by doing the vertical line test. And to be a function, the x's could only have one y value. Well, this 1-to-1 means that the y values can also only have one X value. So that's what we mean by 1-to-1. 1Y, 1X. Okay. So this horizontal line test is a way that we can check that on a graph. And it tells us if a horizontal line can intersect a graph more than once, the graph is not 1-to-1. And remember, by 1-to-1, I meant that each of the Y's can only have one X value. Okay, because if I'm running this horizontal line and it intersects my graph more than once, that means that my Y values are getting two different X's, and we cannot have that. So let's play with some graphs and we'll see if they're 1-to-1. So we're going to use the horizontal line test to determine if 1-to-1. Because y'all, like I said, if a function is going to have an inverse function, it has to be 1-to-1. So my first picture, this graph just sort of starts here and curves up. So the question is this 1-to-1? So y'all remember horizontal lines go straight across. So if you was to draw horizontal lines going across my graph, notice it only intersects it once on that horizontal line. It only intersects it once on that horizontal line. And everywhere I have a horizontal line, it only intersects my graph once. So since it only intersects that graph once, no matter where I draw these horizontal lines, that means, yes, this graph is 1-to-1. Okay. So let's draw another. And y'all, this one will be on y'all. So say I got a graph that does like that. Would that graph be 1-to-1? I forgot my chat. All right, good job, Charlotte. That's definitely a no on that one, because if you used to draw horizontal lines right off the bat, bam, 1, 2, it intersected more than once. So that is definitely a no. All right, let's try one more of those and see what y'all say here. So there's my X and Y. So y'all, this graph want to look like that little squiggly line we were drawing. It's coming up, goes through the middle, and curves up. Is this graph 1-to-1? All right, good job. That is definitely a yes. Because y'all, no matter where I draw that horizontal line, it's only going to intersect it one time. All righty, so remember, for a function to have an inverse function, the graph has to be 1-to-1. So let's look at how to actually find the inverse of a function. So how to find the inverse of a function. All right, y'all, let me let one in real quick. So the first thing we're going to do so that we can actually solve these type of equations, first thing I'm going to do, we're going to replace the f of x with a y. Because remember, f of x really is function notation for a y. But when we solve equations, we really need this y to be in there instead of that f of x notation. So we're going to replace the f of x with a y. Then, just like we did earlier, we're going to swap that x and y around. So we're going to swap the x and y variables. All right, once I swap the x and y variables, I'm then going to solve for that y. So we're going to solve for y. So after I solve for y, I'm going to have y equals something, something. So my last step, I'm going to switch the y back into f of x. But instead of using f of x notation, which was my function, we're going to use what we call the inverse function notation. So we will replace the y with f negative 1 of x. This is what we call our inverse notation. So inverse function notation. Okay, so if my function's f of x, my inverse function will be f negative 1 of x. And y'all, that's the few steps we got to do. The trickiest part is when you got to solve for the y. So these examples will say determine if 1 to 1. Then it says if it's 1 to 1, find the inverse function. Now these start around number 7. And y'all, let me tell you, all of the ones where you got to determine if they're 1 to 1, and if it's 1 to 1, find the inverse function. Every single one of those will be yes, they're going to be 1 to 1. Okay. So from 7 on, they definitely are all going to be 1 to 1. So you'll first click the answer that says yes, it's 1 to 1, and then it'll bring it up, and it'll have that f negative 1 equals, and that's where you're going to put your inverse function. Okay. So let's start out with this one. I got f of x equals x plus 2. So remember, my first step is to replace f of x with a y. So that's going to become y equals x plus 2. So that was step 1. Step 2 said, hey, swap the x and y variables. So I'm just going to swap these variables around. So I'm going to swap the X and the Y. If we do that, we get X equals Y plus 2. So notice I don't move any of the numbers. I'm just swapping them variables around. So what do we say next? We say, hey, solve it for this Y. Well, you ought to solve that, and for the Y, I just got one move to get this Y by itself. I just got to take care of that plus 2. So to take care of that plus 2, I'm going to subtract 2 from both sides. So over here, X minus 2, not like terms. So I'm just going to make that an X minus 2. On the right side, those 2's cancel. All that's left is my Y. So once we've got it solved, MathLab is going to have this F negative 1 of X. All you're going to do is put in your answer. And to get the answer, my last step said replace the Y with the F negative 1 of X. Well, if this is my Y, this equals X minus 2. So you only got to put in what you're getting for your answer. Like I said, MathLab will already have this notation. Now notice what I noticed about these inverses. The original function was being added. Y'all look at my inverse. It's being subtracted. So you'll notice a lot of opposite things going on these, okay? Y'all, these aren't bad. It's just playing with them and getting used to this notation, okay? So let's play with some more. So our number 8 says f of x equals 5x minus 6. All right, remember, first step, replace f of x with a y. So this will become y equals 5x minus 6. Then we're going to swap the x and the y so that we get x equals 5y minus 6. Remember, at this point, all I'm going to do is solve for y. So I want to solve for this y. We got to move that negative 6 by adding 6 to both sides. So we're going to come in here and add our 6. Here on the left side, it gives me an x plus 6. That's going to equal my 5y. And notice, these 6's cancel. So one more step to make that a 5y. We're going to divide both sides by the 5. So y'all, what happens is left side, everything over here is getting divided by that 5. And that's going to equal my 5y divided by 5. So we cannot do anything here. So bring down our x plus 6 over 5. Now look on the right side, those 5's cancel, leaving me my y. So here comes MathLab, f negative 1 of x. So all we do on this one is put in our x plus 6 over 5. Y'all, really, they're not too bad. It's just getting used to the pattern. Switching that f of x into a y. Swapping those variables. And then solving for that y, okay? So of these problems from 7 and on, number 9 might be the trickiest. because they're giving me a fraction. They're giving me f of x equals 5 divided by x plus 9. Okay. So remember, first step, turn an f of x into a y. All right, y'all, what would we do next? Remember, our next move, we're going to swap the x and the y around. So you're going to get a x equals 5 divided by y plus 9. All right, so remember at this point, we want to solve for the y. So y'all, what happens? You remember, if I want this x to look like a fraction, I'm just going to put a 1 under it. But y'all remember while going support, we did some cross multiplying. So to get rid of this fraction, I would cross multiply this. The x on top multiplies by the y plus 9. So you're going to get x times y plus 9. That's going to equal the other side, which is a 1 times 5, which gives me a 5. Now, y'all, 2 ways to do this one. If you want to, you could distribute the x through these parentheses. And that would give you like an xy plus a 9x equals 5. But to me, I do these a different way because I'm solving for the y. So if I want to solve for this y, I want to get this y plus 9 by itself. So what I do to this, since this x is being multiplied by all this, I'm going to take both sides and I'm going to divide by that x. Because y'all notice what happens. If I divide by x, these x's cancel on the left side, and all that's left is a y plus 9. That'll equal the other side, which is 5 over x. Now, you would get the right answer if you did distribute that x, but you would have a little bit more work to do, okay? So this would be like the quickest way. Because now, since I got a y plus 9, if I subtract 9 from both sides, y'all look what happens. My y is now by itself. These 9s cancel. Over here, you got 5 divided by x minus 9. Those are not like terms. So I'm just going to keep that 5 divided by x minus our 9. We're now solved for the y. So our f -1 of x, or our inverse function, will actually equal 5 divided by x minus 9. Hey, y'all, so like I said, they're not too bad. You just got to sort of keep up with all your steps on those. All right, so let's see. I think there's only 12 problems in this section, so it looks like we got about 3 more to go. So I'm going to put my number 10 right here, and I'll move this down a little bit. So y'all, number 10 has f of x equals x to the third minus 4. So, first step, replace the f of x with a y. So y'all are going to have y equals x to the third minus 4. Now that we made that a y, we're going to switch the x and the y around. But remember, we don't move the exponent, it stays. This is just going to become x equals y to the third minus 4. So everything's been swapped. So it's now time to solve for this y. Y'all, let me tell you, when you got exponents like this, so say I had any number a raised to the n. If I just want to make this a, I take roots of this. So I would take the nth root of a to the n. If I do that, if this index matches that exponent, all that's left will be my a. So remember, a while ago, I used exponents to get rid of radicals. Well, to get rid of exponents, we use the radicals, okay? So they undo each other. So the first goal we want to do over here, we want to get the y to the third by itself. So to get the y to the third over here all by itself, I got to move the minus 4 by adding 4 to both sides. So look what that does. The left side gives me an x plus 4. That's going to equal the right side, which has a y to the third. And y'all, them 4s cancel out on the right side. But notice this y to the third now fits this pattern. A could be my y and n can be my 3, okay? So I've now got that pattern going on. So to turn this y to the third into a y, I'm going to take the cube root of both sides. So here we go. The cube root of x plus 4 will equal the cube root of y to the third. So remember, radicals or roots undo exponents, okay? So look over here. You can't do nothing with that. So that's going to stay a cube root of x plus 4. But y'all look at this. This radical cancels that exponent. All that's left is our y. So remember, MathLab will have the inverse notation. Now remember, in MathLab, to get this cube root, you would hit that little radical that has like a blue box above it. So hit that first, and it'll bring in your cube root, and then you just punch in your x plus 4. And y'all, that would be our final answer. So radicals undo exponents, exponents undo radicals. Right, y'all. We're getting down to 2 more of these. So what's this? Number 11. Now this one has a little bit different lingo. This one says f of x is going to equal 3x squared plus 2. And y'all, they got a comma, and it says x has to be greater than or equal to 0. And the reason they're doing this, so let me show you. If you was to graph this whole thing, it's going to make a little parabola coming up, and it would come up on the left side also. So it would make a parabola if you was to graph this, which would fail the horizontal line test. It wouldn't be 1-to-1. But look what they're saying. They're saying, well, we don't want to look at these negative x's. We only want to look at the positive x's. So from 0 to the right on the x's, this thing is 1-to-1 if I'm only looking at 1/2 of it. So to make this be 1-to-1, they're eliminating any of the negative x's. So that's all they mean by this. Because they want us to find the inverse. But like I said, if you don't restrict the domain on this, it wouldn't be 1-to-1. Okay? So if you ever see that, that's all they're doing. They're just saying, hey, we're only looking at the x's that are positive on this. Okay? So they're forcing it to be 1-to-1. All right, y'all. So, like I said, all of these are going to have an inverse. So all we got to worry about is the f of x equals 3x squared plus 2. Well, we're going to replace the f of x with a y. We're then going to swap that x and y around. So I'm going to get x equals 3y squared plus 2. All right, remember, now that I've got these swapped around, we're going to solve for our y. So we need to get this 3y squared by itself. So we're going to subtract this 2 from both sides. So y'all, I get an x minus 2 over here. That's going to equal my 3y squared. And then them 2's cancel. Now, I need this to be a 1y squared instead of a 3y squared. So we're going to divide both sides by the 3. So remember, the x minus 2, all of that gets divided by the 3. That'll equal our 3y squared divided by 3. You know, at this point, can't do nothing over here yet. So I'm going to have an x minus 2 over 3. But on the right side, the 3's cancel, making a 1. So that just gives me a y squared. So y'all, my last question would be, how can I turn a y squared into a y? So that'll be on y'all to figure. Remember, how did I undo these exponents? Square root, good job. So we're going to do a square root x minus 2 over 3 equals a square root of our y squared. Y'all, what's nice, I can't do nothing with this. So that's going to stay a square root x minus 2 over 3. But remember, taking the square root of a y squared, that radical cancels with that exponent, leaving me a y. Now, for some reason, MathLab was being nice on this one because they give you this much of the answer. all you had to do on this one was figure out what's going on the top. Well, all we know what's going on the top is that x minus 2. So yeah, MATLAB will give you the radical, and usually what's on the bottom, all you got to put in is the x minus 2 part, okay? All righty, y'all. So the last one for this 9.2 has f of x equals the square root x minus 3. All right, here we go. Replace f of x with a y. Then swap the x and y around. So you're going to get x equals square root y minus 3. So remember, we wanted to get the radical by itself. And remember that y minus 3 is under that radical, so there's no way to add 3 to both sides when your number is under a radical. So really, what we got to figure out, how are we going to get rid of that radical? So what do y'all think about that one? So no, you don't want to divide on this radical because remember, radicals are different than dividing. But what you want to do to get rid of a radical, I think Sharda said it, you want to square both sides. So exponents undo radicals, just like over here, the radicals undid the exponents. So they sort of undo each other. So like Sharda said, we would come in and we're going to square both sides of this. So can't do nothing with this x squared. But y'all remember, if a radical gets rid of the exponent, well, the exponent gets rid of the radical. And what's left will be the y minus 3. So y'all remember, that's not a divisor there. That's the actual radical. Anytime you got this little notch in it, okay? And remember, we use the 2 because if there's not a number shown in the radical there, it's automatically a 2 in that notch. All right, y'all. Well, we got one more move. We got to take care of this minus 3. So we're going to add 3. So look at that. I get my x squared plus 3 is going to equal my y. So let's see. They're going to give us our f inverse of x notation. And all we got to do is put in our x squared plus 3. Okay. So yeah, that's the big thing on this one. Remember, radicals undo exponents, but they got to match the 2 and the 2, or exponents undo radicals and they got to match. The index of the radical has to match that exponent. All righty, y'all. So that's all the 9.2 is finding your inverse functions. So let me stop my share. All righty, y'all. So now I will take any questions if y'all got it. So today's not too bad. I think this inverse functions is a little bit better than doing those composition of functions. Now, y'all, I will say this. Next Tuesday will be a big day in here because we're going to be solving systems of equations. We're going to we'll start out doing 2 variables with 2 equations. And then that's more to the support part of it. And then we'll end up doing 3 equations with 3 variables. We'll be solving for X's, Y's, and Z's. So those are tricky. So be here Tuesday for those, okay? Y'all, I don't see no questions. So y'all, any questions at all? All right, so I will end this meeting. And if something does come up, email me and I'll get right back with you. So I'm going to stop our